This video is the concept of special right triangles. We have two special right triangles. The first one is actually part of a square. It's half of a square. So we start off with a square, and then we put one diagonal in it. Cut that into two right triangles, and each of those right triangles are considered special right triangles. First of all, that diagonal bisected those angles, so each one of those triangles has two angles that are congruent of 45 degrees, so it makes it a nice isosceles right triangle. And the two sides have the length of x. The hypotenuse of the right angle, the right triangle, is a y. It's an unknown, but I do know that whatever the legs are, that they will be the same because it started off from a square. So using the Pythagorean theorem, we could write that x squared plus x squared equals y squared. And combining like terms, we've got 2x squared equal y squared. We can take the square root of both sides, and we can find that y is equal to x square root of 2. So we could write all three sides of that right triangle using the letter x. And what we know is that the angles of that right triangle, the special right triangle, are 45, 45, and 90. And so we call it the special right triangle. We call it a 45, 45, 90 degree right triangle, even though that's a little redundant, but we say 45, 45, 90 degree triangle. The sides, therefore, using the letter x, have the ratios of x, x, and x root 2, where x root 2 would be the hypotenuse. So let's say it was a square with sides of 3. So the sides of the triangle would be 3, 3, 3 root 2. If the square had sides of 4, then this would be 4, 4, 4 root 2. If the square had sides of 10, it would be 10, 10, 10 root 2, etc. So this is one of the special things about the right triangle, is we can put all three sides in relationship to this one variable x. In your textbook, they use the letter L, so I just want to make sure you see that in the textbook, they're going to say a 45, 45 degree, 90 degree triangle has leg measures of L, so they'd have L, L, and then the hypotenuse is L root 2. It doesn't make any difference what variable we use. It's the same idea. So our second special right triangle, again, there's only two of them, is half of an equilateral triangle. And remember that an equilateral triangle is a triangle where all three sides are congruent. And we also know, we have some theorems that tell us that an equilateral triangle is also equiangular, so all three angles in that triangle are 60 degrees. Well, we're going to cut that in half with an angle bisector, or a median, or a perpendicular bisector, whatever you want to call it, because in an equilateral triangle, all of those perpendicular bisector, angle bisector, median, and midsegment, they're all that same red line. And that divided that equilateral triangle exactly in half. It bisected the angle, the vertex angle there, so we now have a 30 degree angle, and it also bisects the sides down the base there, so that if I called each of those halves x, that would mean that the sides of this equilateral triangle would be 2x's. And what I'm really interested in is that right triangle that I see has a 60 degree, a 30 degree, and a right angle, 90 degree angle. And I see that I have two sides. One of them is an x, and the other is a 2x. And we don't know what that red line is, that we're going to call that y. But we have those, so we have three letters for three expressions for the three sides of the right triangle: x, 2x, and y. Well, we're going to use those in the Pythagorean theorem. We're going to say that x squared plus y squared, the two legs of that right triangle, squared, equals 2x quantity. The parentheses are very important there. 2x quantity squared. We're going to simplify that. We get x squared plus y squared equals 4x squared. And we will subtract the x squared from both sides, so that we have y squared equals 3x squared. Taking the square roots of both sides, we can solve for y. And now we can write y in terms of x. And so that red length in there that divided that equilateral, that side, one of the legs of the right triangle, could be written as x root 3. So in that special right triangle, we have angles of 30, 60, and 90 degrees. And the sides have a ratio of x for the shortest side, x root 3 for that third side that we found, and 2x for the hypotenuse. And that's really important, that that 2x is the longest side and it's the hypotenuse. Another way we describe the relationship in this 30, 60, 90 degree triangle is that in a 30, 60, 90 degree triangle, the hypotenuse is twice the length of the shortest side, and the third side is root 3 times the short side. So this is the ratios and some important information about special right triangles. I'll give you a second video on how to use this because that's very important. We're going to be using this quite a bit.